The craters of the Moon. Once it was thought they were formed by volcanic upheavals. The true cause is impacts from space. Mercury is the most heavily cratered planet, each pockmark recording a smack from the heavens. Most impacts happened when the planets first formed. These are Martian craters, imprints of primordial debris. From 4.5 billion years ago, the solar system was a maelstrom of colliding bodies, a bombardment that lasted 600 million years. But on our serene planet, where are the impacts? We have them, if you know where to look. Australia, dry and geologically stable, is one of the best places to find a crater. In the heart of the outback, these are the Henbury craters. They were blasted by an impactor that had broken into pieces. Most craters on Earth are quickly eroded by weather. These survive. The Henbury impacts happened just 5,000 years ago, evidence that Earth and the Moon are still threatened by projectiles from space. To find their source, we travel away from the Sun. Through space long cleared of interplanetary trash, we head beyond Mars. Out here, in the great void before Jupiter, is the asteroid belt. It's a vast disk of rocks, a ring of so-called minor planets. Were it not for the disruptive pull of Jupiter, the asteroid belt might have formed a single planet. As it is, orbiting between Mars and Jupiter, the belt is an array of potential projectiles. Gaspra is a typical asteroid. 20 kilometers across, composed of silicates and pure metal. Imagine it plunging to Earth. This one, called Ida, is twice the size. So big, it has a tiny moon on the right, named Dactyl. Dactyl, a chip off the old block. Twice the size again is Matilda, 52 kilometers wide. Blacker than coal. It's the darkest we know. In false color, Vesta, brightest of all the asteroids. It's big, 530 kilometers in diameter. The dark part is a gigantic crater. Proportionally, if Earth had one similar, it would span the Pacific Ocean. Occasionally within the asteroid belt, there are collisions. Some of the resulting fragments can be ejected into orbits that carry them closer to Mars. Then, in repeated passes of Mars, an asteroid may be nudged into a new path, a trajectory that crosses the orbit of Earth. Such an asteroid has struck. 65 million years ago, it hit Mexico's Yucatan Peninsula. The result was a cosmic winter and mass extinction. When the skies cleared, 2/3 of all species were gone, including the dinosaurs. In false color, this is the crater, buried now beneath forest and ocean. The crater is 200 kilometers wide. The asteroid, which penetrated Earth's crust, was at most 15 kilometers wide. Earthly craters are best identified from space. This one has filled with water and formed a lake. Here, 2 lakes in 2 craters. And here, in crater-rich Australia, Wolf Creek. Preserved in the arid outback, the crater is 850 meters wide and some 300,000 years old. But that's young and modest compared to Australia's greatest impact site, which dates back 142 million years. Goss's Bluff, well over 20 kilometers across. In the United States, this is Meteor Crater, Arizona, gouged 50,000 years ago by a chunk of nickel and iron. Smaller projectiles reach us every day. Like this fireball, most burn up in the atmosphere and never make the ground. They can steal the show at a football match. Each year, 16,000 tons of debris rains from space. If a chunk lands, like this one, it's called a meteorite, burnt black in its fiery descent. This piece of solid iron was recovered when a meteorite detonated over Russia's Far East. It peppered the ground with cosmic cannonballs. Over North America, this one grazed the atmosphere and returned to space. Meteorites pose little threat. Asteroids do. A 1-kilometer projectile could wreak havoc. A dinosaur killer would wipe us out. So how do we protect our planet? The front line is here in New Mexico, where telescopes watch for intruders. The project, named Linear, is a joint venture of NASA and the United States Air Force, an automated system that scans for new asteroids. Thousands have been logged. Of crucial interest are near-Earth objects that are moving fast. An asteroid that could threaten the planet. Once identified, radar takes over. Dishes of the Deep Space Network bounce radio waves off Earth-crossing bodies. Size, shape, and rotation are logged. We must know the enemy. This one, Castalia, is like a peanut, possibly 2 asteroids touching. And like this one, Geographus, up to 1,000 near-Earth asteroids are more than 1 kilometer wide. Eros is the asteroid we know best, for we've paid a visit. This is real movie. Eros is 33 kilometers long. A space probe called Near Shoemaker has taken 160,000 pictures and seen 100,000 craters. With such a battering, it's not surprising the surface is like rubble, but the interior is rock solid. In 2001, the spacecraft landed on Eros. We've touched the enemy. Luckily, this flying colossus doesn't threaten Earth. But inevitably, there's an asteroid that does. And if we're vigilant, we may have time to deal with it. One idea is a curved reflector. We could focus the rays of the sun on a small spot. By causing a jet of material to erupt, the asteroid will be driven from harm's way. Another approach could be a little rocket driver. Like an outboard motor, it will be attached to the threatening asteroid, moving it to a safer orbit. But if time were really short, and we'd be hit within days, there's the nuclear option. A warhead could blast the asteroid. Trouble is, we might then have a shower of fragments heading our way. There's a cleverer idea. Instead of approaching head-on, we could launch a warhead to one side of the asteroid for a standoff detonation. If the calculations are right, the projectile would be shunted from its collision course. Currently, our planet is safe. None of the Earth-crossing asteroids so far identified is a threat. There are scares, but within days, when orbits are refined, new sightings have proved harmless. The great moons of Jupiter. Discovered 400 years ago by the astronomer Galileo, the 4 largest moons are so big they were discernible through his primitive telescope. Jupiter has at least 60 moons, many mere chunks of rock. With 3 rings of dust as tenuous as gossamer, Jupiter is more than 5 times farther from the Sun than is Earth. Out here, it takes nearly 12 years for a solar orbit. Jupiter is the biggest planet. Earth would fit 12 times across a diameter of almost 143,000 kilometers, and Jupiter could swallow Earth 1,323 times. Another vital statistic: while Earth, not to scale here, has a tilt of 23.4 degrees, Jupiter leans at just 3 degrees. In mythology, Jupiter rules heaven and earth, but compared to the Sun, Jupiter is a lowly lord, too puny to qualify even as a failed star. Yet Jupiter is bigger than all the other planets combined, a ball of gas, 90% hydrogen, the rest mainly helium, spinning on its axis in less than 10 hours. En route for Saturn in the year 2000, the Cassini spacecraft imaged the vast weather bands of Jupiter. The white and yellow zones are high cloud, the red and brown belts low cloud. The bands blow in opposite directions. Time-lapse shows eddies and storms racing round the planet. The bands are all we see of this world without a solid surface. Lower left is the Great Red Spot, a tempest that's raged for centuries. It's an anticyclone, 3 times the size of Earth. Cassini showed the polar regions. With less banding, the weather is quieter. (1989), and Space Shuttle carries aloft Galileo. 6 years later, Galileo drops a probe into Jupiter, a colossus whose average density is like potato soup. First encounter, the stratosphere, thin and bitterly cold. Beneath are ice clouds, as pressure approaches that on Earth. Lower, through stinking gas, pressure and temperature build. Then, surviving winds and lightning, the craft is lost in an atmosphere 18 times denser than Earth's. In 1 hour, the probe had penetrated only the atmospheric skin. Jupiter has 5 cloud layers. Topmost, the wispy stratosphere. Beneath, ammonia ice crystals. In the middle, smelly ammonium hydrosulfide. Then water ice crystals, and below water like a deep warm ocean on Earth. The atmosphere disappears in the layer beneath. At 2,000 degrees and 1,000 kilometers deep, hydrogen turns liquid. Deeper still, hydrogen becomes a metallic liquid. At the rocky core, it's 20,000 degrees. Jupiter's vast magnetic field springs probably from the internal layer of metallic hydrogen, which conducts electricity. At the poles, the result is aurorae. Charged particles drawn from space interact with the upper atmosphere. Jupiter's magnetic field is the biggest in the solar system. If we could see them from Earth, the force lines would appear as big as the Moon. Like a donut in the magnetic field, a ring of electrically charged particles, the Io torus. It carries 2 trillion watts of power. The cause is the moon Io, which orbits in the Io torus. Having dropped its probe into Jupiter, Galileo flew by Io in a series of loops around the planet. Io is the closest major moon. Larger than our moon, but unlike the moon, Io has no craters. The reason is volcanic activity. Constant eruptions, here in blue, renew the surface, and they feed charged particles into the Io torus. Io's surface is a sizzling pizza, the most volcanically active in the solar system. The cause is probably gravitational flexing, the pull of both Jupiter and the moon Europa. This moon is Jupiter's biggest, Ganymede, with a diameter of more than 5,200 kilometers. Set against the planet Mercury, Ganymede is bigger. Its largest feature is Galileo Regio, the dark disk. Rich in impact craters and grooves, the ridges are a kilometer high. Galileo detected a weak magnetic field and clues to Ganymede's interior. Beneath the crust are possibly a slushy sea, a layer of rock, and a metallic core. Another Galileo encounter, Callisto. Outermost of the big four, Callisto is heavily cratered. This, the Valhalla Basin, 3,000 kilometers wide. Another impact site, the Asgard Basin. Callisto is thought to have a crust of ice and rock overlaying, some believe, a salty sea. Jupiter's fourth great moon is Europa. Europa is an extraordinary world, crisscrossed with icy ridges and glacial ravines. They're caused as icy plates break up and shift. White material is water ice. Red is dirty ice containing salts or silicates. These freckles suggest warmer ice is churning from below, while colder ice is sinking. Like this sea ice on Earth, Europa's shell may well conceal an ocean. And what an ocean! Bottled up below an ice crust that may range in thickness from a few meters to several kilometers. A deep ocean, salty and warm, heated by tidal stresses from Ganymede and Io. As in earthly oceans, hydrothermal vents may spew volcanic gases. Best evidence for the ocean came when Galileo detected electrical currents beneath the surface. That inspired several ideas. This one, still in development, is a mission to Europa along with Callisto and Ganymede, which may also have oceans. It's called the Jupiter Icy Moons Orbiter. First scanning Callisto, data will provide comparisons with Ganymede, the second target. How did they evolve? Can oceans be proved? Could they sustain life? At Europa, the same questions, plus, where's the thinnest ice? Later, another craft will be dispatched to Europa, this time with a lander. Armed with information from the recce, touchdown will be where the crust is thin enough to bore into the ocean. Deploying a robot submarine, a hydrobot, there'll be a search for life. If simple organisms are found, they could have evolved, as in our oceans, around hydrothermal vents. From the tiny craggy moon Amalthea to giants like Io, Jupiter rules a mini solar system. Europa, like Earth, may have oceans and life. Ganymede, like Jupiter, is the biggest in its system. Callisto, like Mars, is outermost of its class. Farther out, a swarm of little moons, altogether 70 and rising. The river is liquid ethane. The temperature is minus 180 degrees Celsius. The lake is liquid hydrocarbons, and there are black deposits of tar. The atmosphere is worse than the smoggiest city on Earth, nitrogen laced with the likes of propane and acetylene. The mist is methane. This is Titan, the greatest moon of Saturn. Such an exotic moon sits well in this dazzling domain. Saturn, Lord of the Rings, God of the Harvest, is sixth planet from the Sun, taking almost 30 years to complete an orbit. Second largest planet, Saturn's diameter is 120,000 kilometers, the width of 9 Earths. Saturn could accommodate Earth 752 times, far fewer than Jupiter. Saturn has a tilt. Earth leans at 23.4 degrees, Saturn at 27, but what style? Were there a glass of water big enough, Saturn would float, for the planet is a ball of gas, just 7/10 the density of water. Like Jupiter, Saturn has no solid surface, just weather bands. White is high cloud, yellow lower cloud. In false color, the bands are hazy, less defined than on Jupiter. It's because Saturn's cloud lies lower in the atmosphere. 2 anticyclones, whirls of high pressure. And a jet stream. Saturn has the strongest winds. And it spins so fast, once in less than 11 hours, that Saturn, like Jupiter, bulges at the equator and is squashed at the poles. Saturn is 94% hydrogen, the rest mainly helium. There are 5 cloud layers. Topmost, the diffuse and hazy stratosphere. Then, ammonia ice crystals. Ammonium hydrosulfide, ice crystals of water, and finally droplets of water. The deeper in, the hotter and denser it gets. At over 1,000 kilometers in, hydrogen goes liquid. Beyond 25,000 kilometers, it's metallic. The rocky core is 15,000 degrees. Saturn's magnetic field is probably due to electrical currents in the liquid metallic hydrogen. A result is aurorae around the poles, as the magnetic field traps electrically charged particles from the solar wind. The particles are drawn downwards by force lines to react with the atmosphere, particles that have traveled 10 times farther than Earth is from the Sun. The rings of Saturn. Less than a kilometer thick and 500,000 wide, they're reason enough for manned spaceflight. The brightest rings, those we can see through a telescope, would stretch from Earth almost to the Moon. The darker rings, which we can't see, stretch much, much farther. From Earth, our view of the rings and the sunlight they reflect change as Saturn orbits the Sun on a tilted axis. Here, they appear almost edge-on. Then, gradually, through the season, they open. The gap in the rings is called the Cassini division. This smaller gap, the Encke division, is in Saturn's so-called A ring. There are 7 rings, each with a letter. This is the C ring, less sparkling than A and B. Like all the rings, it's comprised of hundreds of ringlets. Time-lapse of the B ring, the broadest and brightest. The dark spokes are possibly dust, levitated by electrostatic forces. So close are the rings to Saturn that its gravitational tug prevents them forming a moon. Instead, they're swarms of moonlets, from grains of dust to rocks the size of tanks. The rings may be the debris of a moon that came too close, or of moons that collided. Either way, eventually, they'll fall into the planet. 3 rings, D, E, and G, are dark and virtually invisible. The thinnest, ring F, is just beyond ring A, and kept on the straight and narrow by a couple of shepherd moons. Saturn has more than 30 moons, and the list keeps growing. As with all gas giants, moons are the only solid and tangible bodies. Mimas may be tiny, but we could land there. An impactor once did and dug a great crater. Had it been bigger, Mimas would be dust. Enceladus is twice as big, but still just 500 kilometers wide. Dusted possibly by icy particles from Saturn's E-ring, the surface is highly reflective. Equally icy and twice the size again, Tethys, a fault line almost girdles the moon. A little larger and with a big crater, Dione is icy, riven and battered. Even its fault lines are eroded by impacts. A close-up of Rhea, diameter 1,500 kilometers, an ancient surface recording 4.5 billion years of impacts. This is Hyperion, a fuzzy image, but undeniably the spitting image of a bath sponge. Next out, dark markings on icy Iapetus, 1,400 kilometers wide. And odd little Phoebe, which orbits in reverse. In a class of its own is Titan, Saturn's single big moon. Larger than Mercury, Titan's dense atmosphere shrouds the surface. But the haze has been penetrated in near-infrared. The Hubble Space Telescope has revealed two distinct surfaces. They may well correspond to land and oceans. This could be the picture. Seas of liquid hydrocarbons, rocks coated in hydrocarbon sludge, an atmosphere like Earth rich in nitrogen but 10 times denser, a choking smog as sunlight breaks down methane. Methane breakdown is known to produce organic molecules. The question is, do they form long-chain proteins with a potential for life? Is Titan early Earth in deep freeze? To find out, this mission launched in 1997. Cassini, as it's called, was the heaviest craft ever to blast into space. 3 years later, it reached Jupiter, having swung twice by Venus and once by Earth for gravity assist. With another push from Jupiter and another 4 years, Cassini aims a lander at Titan. It's part of a 4-year program, because Cassini's overall objective is to survey the whole Saturnian system. The probe named Huygens hits Titan's deep atmosphere. Then, braking by parachute, Huygens samples the smog. For relay to Earth, data is radioed to the mother craft, Cassini. Huygens must land gently. The icy surface is like steel. With no sun for solar cells, Huygens has just 30 minutes of power. As it snows ethane and methane, data is transmitted live. And if it's a splashdown, Huygens can float. The landing, all being well, is in 2005. Whether or not Titan yields up the building blocks of life, it'll be a long time before human life comes face to face with the Lord of the Rings. (1977). Voyager 2 leaves Earth on the greatest expedition ever. With Voyager 1 just behind, twin probes en route for Jupiter. Then, with gravity assist, a change of course for Saturn. Here their paths diverge, Voyager 1 leaving the planets, Voyager 2 slingshotting onward. Uranus is reached, 9 years out from Earth. And Neptune 3 years later, in 1989. With gravity assist, Voyager 1 picked up 48,000 kilometers an hour from Jupiter. From Saturn, and an alignment of planets that happens once in 176 years, Voyager 2 sped on to Uranus. Each slingshot infinitesimally slows the planet. Voyager 2 reached Neptune in 12 years. Without gravity assist, it would have been 30, a distance so great, radio signals took over 4 hours to reach Earth. Gold-plated discs on both Voyagers carry earthly information to the stars, but the craft must speed thousands of years to reach even the nearest star. From our star, the Sun, it's 2.8 billion kilometers to Uranus, exactly twice the distance of Saturn. Voyager 2 got the first close-ups. Uranus, a bland ball of gas, has rings. They were discovered when astronomers saw a star winking as it passed behind the planet. The rings, 11 at last count, are dark and narrow. Uranus is a giant. 4 Earths would fit across its girth. But against Jupiter, Uranus comes a modest third, after Saturn. All the same, Earth would fit inside 64 times. Uranus spins backwards at a crazy tilt. Earth leans some 23 degrees, Uranus at 98. Voyager found it featureless, even in false color, little but haze around this pole. But when the Hubble Space Telescope came on stream, it used near-infrared to reveal weather and pink clouds of methane. The cloud tops are minus 220 degrees Celsius. Beneath are 4 layers of cloud. Topmost, hydrocarbon smog. Then methane and hydrogen. Ammonium hydrosulfide. A transition zone, gas merging into liquid. And the interior, hydrogen and helium mixed with slushy ice. Deeper still, the mix is probably slushy water and methane. And oddly, for a gas giant, the rocky core isn't very hot. Even stranger is the magnetic field. It has a severe tilt and runs through one side of the planet, due probably to force lines springing not from the core, but from overlaying slush. From above, the moons and rings of Uranus. Most rings are less than 10 kilometers wide, made of particles like lumps of coal. This may be their origin. Shattered by an impact, the moon Miranda could have formed the rings, and then, from the bulk of the debris, put itself together again. A much bigger collision from a body the size of Earth is thought by some to have tipped Uranus sideways early in its history. Both ideas are unproven and have critics, but a moon reassembled would well explain the chaotic contours of Miranda. This icy world, just 480 kilometers wide, is a geological wonder. Some believe the ruggedness is partially melted ice rising from beneath. Here, at the biggest rift, cliffs are 15 kilometers high. To fall off in Miranda's weak gravity, it would take 14 minutes to hit the ground. The moon Ariel, over twice the size, is also cut with rifts. Umbriel, a little larger, has an ancient cratered surface. Titania, the biggest, is over 1,500 kilometers wide. Oberon, slightly smaller, is outermost of the big moons. In mythology, Uranus is the father of Jupiter and Neptune. For Voyager 2, Neptune was the next stop. God of the sea and last of the gas giants, Neptune is so remote it takes 165 years to orbit the Sun. Trouble in predicting the position of Uranus led to the discovery of Neptune. Uranus, on the second outermost orbit, was rarely where astronomers thought it should be. Here, Uranus gains speed as it catches up with Neptune. But after overtaking, Uranus slows again. That was it. The pull of Neptune was perturbing the orbit of Uranus. By taking these disturbances into account, astronomers discovered Neptune. Needing 4 Earths to span its diameter, Neptune is much the junior of Jupiter, but only slightly smaller than Uranus. It would take 58 Earths to fill Neptune, 6 fewer than Uranus. But Neptune has more density and mass, and it's the right way up. Earth tilts at 23 degrees, Neptune at almost 30. After the haze of Uranus, Neptune offered Voyager real features. Most prominent was the Great Dark Spot, a tempest just south of the equator, an anticyclone edged with feathery cloud. Constantly changing shape, the storm turned on its center every 16 days. Farther south, a cyclone called D2, or the Wizard's Eye. Neptune is a very windy place. Here, cirrus clouds are streaked in bands across the upper atmosphere. An hour faster than Uranus, Neptune's interior rotates in 16 hours, 7 minutes, but different bands turn at different speeds. It's because Neptune isn't solid, plus strong equatorial winds blow against rotation, while some others go with it. After Voyager, the Hubble Space Telescope tracked the weather, and the Great Dark Spot had gone. 6 years later, when Hubble looked again, Neptune had brightened. Like Uranus, the cloud tops of Neptune are minus 220 degrees, and the layers are similar. Uppermost, hydrocarbon haze. Then methane mixed with hydrogen. Frozen ammonia raining on stink bomb gas. And a transition zone where gas becomes liquid lower down. To the interior, hydrogen and helium mixed with slushy ice. Beneath is more slush, water ice and methane, and radiating more heat than it gets from the sun, a hot, rocky core. Neptune has the weirdest magnetic field. With a tilt of 47 degrees, its axis is closer to the surface than to the core. And like all gas giants, the force lines have an opposite polarity to Earth's. Neptune has 2 main rings and a third, just discernible, on the inside, closer to the planet. Curiously, the outer ring varies in thickness. In some places, material has clumped to form arcs. Neptune has 10 tiny moons and a single big moon, Triton. 2,700 kilometers wide, Triton's highly reflective surface has the greatest diversity of ices anywhere, and at minus 235 degrees, it's the coldest place known. The little heat that's not reflected melts nitrogen beneath the surface. As a result, gas bursts through and is carried far downwind, high in the wispy atmosphere. We are 4.5 billion kilometers from the Sun. Dark, diminutive and cold. Farthest planet from the Sun. The frontier world of Pluto, so obscure it wasn't spotted until 1930, or its moon, Charon, until 1978. Pluto was discovered by a country boy from Kansas in the United States, Clyde Tombaugh. Tombaugh was the first to find a planet since Neptune in 1846 and Uranus in 1781. Bored with farm life, Tombaugh had caught a train. A one-way ticket from agriculture to astronomy. He'd been offered a job as an observer at Flagstaff, Arizona, in the Lowell Observatory. Tombaugh had impressed them with observations from his home telescope. Now, climbing the hill to Lowell, he was to join the hunt for Planet X. It was the obsession of the observatory's founder, Percival Lowell, but Lowell had died, frustrated in his quest, 14 years earlier. The search, however, continued. Lowell had been convinced of Planet X. He thought it affected the orbital motions of Uranus and Neptune. But he had a reputation for mistaken observations. There were announcements of comets, never confirmed, and canals on Mars, built, he believed, by intelligent beings. The search for Planet X had been going 25 years when Tombaugh arrived. This quaint little telescope would be his window on the heavens. Night by night, the sky was photographed on huge glass plates, exposures lasting several hours. It was grueling and perishing in winter, the 13-inch lens systematically gathering data. But after a fruitless quarter-century, morale was low. Tombaugh was a fresh pair of eyes. And soon he had an extra job, comparing images of the same tiny piece of sky taken several nights apart. By blinking them, he could spot objects moving within the solar system against the background stars. The work was meticulous. Tombaugh recalled working the plates like a hayfield. Each strip of sky contained thousands of objects. Each frame of each strip had hundreds, everything from galaxies to star clusters. He probably viewed more of the universe than any other astronomer. In looking for his cosmic hayseed, Tombaugh viewed 45 million objects. After each half-hour's viewing, he'd break for 15 minutes. The concentration was immense. But after 6 months of blinking, Tombaugh found a dot that jumped. Suppressing his excitement, he checked and rechecked the plates, then made for the office of the director, V.M. Slifer, for the historic announcement.
Dr. Slifer, I found you Planet X. He rose right up out of his chair like from a spring, and with a look of delight and also reservation.
Slifer ordered sealed lips and immediate re-photography. That evening, February the 18th, 1930, was overcast. Tombaugh dined at his favorite cafe. He saw a movie, Gary Cooper in the Virginian, hoping skies over Flagstaff would clear. But after midnight, the moon rose. Observation and photography were now impossible. At 1:30 a.m., Tombaugh went to bed. But next evening, he got his shot. The object, as expected, had moved a little from its earlier position. Clyde Tombaugh, aged 24, had found Planet X. But the observatory played down his role. Even today, locals get the name of the discoverer wrong.
Say Percival Lowell.
Lowell.
Percival Lowell.
Lowell.
Lowell?
Percival Lowell.
Lowell cast a long shadow. Planet X, or Pluto as it was named, was undeniably his hunch. But it was the insight and rigor of Tombaugh that had found the planet. He'd restored the observatory's reputation. Even so, Director Slifer dismissed Tombaugh in 1945, pleading shortage of funds. It was a bitter pill, for Tombaugh, eager to resume research, had just returned from a teaching secondment during World War II. 50 years on, he still believed Pluto was the reason.
He was jealous because I found it, he didn't.
Flagstaff's loss was the military's gain. Tombaugh went into rocket development at White Sands, New Mexico, precursor of the NASA space program. A decade later, he was back in observational astronomy. At New Mexico State University, Las Cruces, he had an astronomy department and a telescope. The professor who'd found a planet. And Pluto is no ordinary planet. Its orbit tilts relative to the other planets, and that orbit is an eccentric ellipse. At its closest to the Sun, here, Pluto is just inside the orbit of Neptune. At its farthest, here, Pluto is way outside. It swings so wide, Pluto takes almost 250 years to orbit the Sun. Pluto has a moon, and it's named after this woman. Her husband, Jim Christie, discovered the moon during routine research.
A lot of husbands promise their wives the moon, but Jim delivered.
Jim Christie had ordered photographic plates from this telescope at the US Naval Observatory in Flagstaff. From the images, he deduced Pluto had a moon. After his wife, he proposed the name Charon. In mythology, Charon is the ferryman to Pluto's underworld. On this plate, there's no sign of Charon. But on this one, Pluto is elongated. The bulge is Charon, proportionally a big moon, 1/5 the mass of Pluto. Together, they're like a double planet, locked in a super-synchronous rotation less than 20,000 kilometers apart. They orbit each other in 6 days, 9 hours, movements that revealed Pluto much punier than expected. It's tiny compared to Earth. Even our moon has 6 times the mass. Lowell was wrong. Pluto hasn't the mass to affect the orbits of Uranus or Neptune. Not to scale here, Earth leans on its axis by 23.4 degrees. Pluto tilts at 122 degrees. As Pluto and Charon move round the Sun, their aspect from Earth changes. Only here, when Charon's orbit is edge-on, is it good for astronomers, because at other times, Charon doesn't eclipse Pluto. Eclipses are important. They're windows when astronomers can learn most about Pluto's surface. There were many, as here, between 1985 and 90. From the most powerful telescopes on Earth, this was our best view. But from the Hubble Space Telescope, we could see regions of varying brightness. Scientists believe the surface is ice, the interior a mixture of rock and ice. From the Sun to the closest point of Pluto's orbit is almost 4.5 billion kilometers. To the farthest point, over 7 billion. That's well into the Kuiper Belt, a disk of icy fragments whose largest member is Pluto. There may be 100,000 such bodies over 100 kilometers wide. This is New Horizons, a space probe planned for Pluto. By 2015, the craft is to send pictures and data from the only worlds in the solar system yet to be investigated, Pluto and Charon. Thereafter, New Horizons will probe the Kuiper Belt. Clyde Tombaugh won't see the results. He died in 1997, the last man to find a planet. Would he have visited? No, sir. Too many cold nights at the telescope. With solid methane detected, Pluto is colder than -200 degrees Celsius. And as it swings from the Sun, even the atmosphere freezes. As Earth turns on its axis and the constellations appear to move across the heavens, there's more to the night sky than the stars, the planets, and the moon. There are visitors that can shine brightly for weeks, nomads whose unpredictability makes them all the more exotic. We know them as comets. To understand comets, we return to the earliest solar system. At the hot center, heavier elements condensed, like metals and rocky silicates. The inner planets are rich in such elements. But farther out, where it's cold, through the gas giants and the Kuiper Belt, lighter elements condensed. They formed ices of methane, water, and ammonia, and still farther out, a shell of icy bodies called the Oort cloud envelops the solar system. It's from Oort and Kuiper that comets fall. Dislodged perhaps by the gravitational twitch of a neighboring star, a comet is drawn inwards by the tug of the Sun. In the unaccustomed warmth, as ancient ices vaporize, they stream off as a great tail. Rounding the Sun, the comet is now captured in a vast elliptical orbit. Time-lapse of a comet shows a tail fluorescing blue because of the ultraviolet of sunlight. Comets grow two tails. The blue is gas, the yellow, dust. The gas tail can disconnect if there's a gust in the solar wind, and then reattach. The tails disappear as a comet returns to the freezing outer reaches. But when displayed, the tails always point away from the sun. The blue gas tail is blown by the solar wind, electrically charged particles that stream from the sun. The tail can stretch 100 million kilometers from the comet's head. The broader and shorter dust tail is pushed outwards by the radiation pressure of sunlight. Dust from the tail litters the wake of a comet. When intersected by Earth, grains streak into the upper atmosphere and burn up. We see them as showers of meteors or shooting stars. It's impossible to watch comets near the sun. But blank it out, and there they are. Here's one with a solar eruption. Some don't make it. Comets careen through the planets on random orbits. The sun is their master, but watch the red one. Because Jupiter has an influence too, the comet is locked into an ellipse by the two major bodies of the solar system. Here comes a sun plunger and a sun grazer. Comets come from all directions because they start in all directions. The Oort cloud is a far distant bubble around the planets. Jupiter's massive pulling power captured this comet, then tore it to pieces. Shattered into 20 or more fragments, the comet had passed within 30,000 kilometers of the mighty planet and paid the price. It was photographed in 1993 like a string of pearls. Named Shoemaker-Levy 9 after its discoverers, excitement mounted, for the comet was on a collision course with Jupiter. Sure enough, through a week in 1994, the fragments tore into the planet at 60 kilometers a second. They exploded in the soupy atmosphere at 10,000 degrees Celsius. From Earth, the impacts were out of sight. After each hit, astronomers had to wait until the planet's rotation brought the scar into view. In infrared, the fireball from an impact. For a few days, Jupiter had a battered face. The largest fragments were 3 kilometers wide, but pinpricks to this gas giant. Had they hit Earth, it would have been catastrophic. And comets do hit us, the last one over Siberia in 1908. Exploding in the atmosphere, uninhabited forest was flattened. The likely cause? A comet fragment. Were this a city, millions would have died. Halley is the most famous comet, captured by Jupiter into a short period orbit 200,000 years ago. Since then, Halley has returned to our skies, on average, once every 76 years. Halley's ellipse brings it from beyond the orbit of Neptune, when farthest from the Sun, to within the orbit of Venus, when closest to the Sun. At its last appearance, Halley moved through our skies like this, on its way to the Sun late in 1985, and back out in early '86. Halley appeared in medieval skies when in 1066 the Normans conquered England. This from the Bayeux Tapestry. Halley was the star of Bethlehem in Giotto's fresco. He'd seen the comet in 1301. That comets are periodic in return was predicted by Edmund Halley. He saw the comet in 1682. Halley's comet, as it became, was first photographed on the return of 1910. And when it reappeared in the 80s, the space age had a welcome. An international armada headed for a rendezvous. 2 probes were Russian, 2 Japanese, and 1, named Giotto after the painter, European. Giotto flew closest of all, right through Halley's coma, the halo of gas and dust that vented from an icy nucleus 16 kilometers by 9. In 1998, an American blastoff for another short-period comet. Just 8 kilometers long and hewn like a bowling pin, this is Borrelli's comet. Long-period comets, like Comet West, can be spectacular. Here's another, Hyakutake, and because of their long periods, they appear unexpectedly. Hale-Bopp, which surprised us in 1997, stole the show for months. From a nucleus 40 kilometers wide, Hale-Bopp spiraled gas and dust. To the right is the orbit of short-period Halley. Compare it to the long period of Hale-Bopp, an orbit of thousands of years. Not a celestial paddlecraft, but a probe named Stardust, whose job is just that, to collect interstellar dust. But its other task is to catch Comet Wild 2 and its emissions. With this collector, particles will be trapped and returned to Earth for analysis. The first consignment from a comet. Scientists will dissect matter predating the solar system, as well as comet grains from its birth. Another comet, another probe. The European craft Rosetta is to orbit the comet Churyumov-Gerasimenko as it heads for the Sun. America's Deep Impact will be equally bold. It's to launch an impactor towards the comet Tempel 1. The idea is to blast a crater the size of a stadium and see what's inside. As the oldest objects in the solar system, comets hold clues to its birth. Comets may have carried water to Earth and sparked life. Perhaps 100 billion comets remain in the Oort cloud, all awaiting a tail-trailing tumble to the Sun.